Um, Good morning, everyone, or afternoon, I guess. Um, Today, we've got a few things on the agenda. I hope you've already had a chance to see the homework reviews that were posted for problems 7 and 8 in the textbook. And that's in preparation for the quiz that will be on Wednesday of next week. And we'll have a practice quiz problem that we'll do in class on Monday, which is an even day, not an all day. Um, what I want to do today is review a couple of things and kind of get you set up with a system that I think will be helpful for you in dealing with problems involving Newton's second law. Um, so we're going to look at just the general relationship between Newton's second law, equilibrium, and dynamics, and then think about how to actually solve problems where the sum of the forces is not zero. In other words, there's an overall force on an object that results in acceleration. So equilibrium is primarily what we've been focused on so far, and equilibrium is still based on Newton's second law. If you sum the forces on an object using vector mathematics, if they all end up sort of canceling each other out, and you end up with a force of zero, then you have a situation where an object is in equilibrium. There's no net force and no acceleration. Newton's second law says that if you sum all the forces on an object, it should be equal to that object's mass times its acceleration. And just as a reminder, when we are dealing with mass, we always use the unit kilograms in this formula. If you don't use the unit kilograms, it's not that the numbers you get are incorrect. It's just that your forces won't be in newtons. Your forces will be in a different unit, and things get off by a factor of potentially 1,000 if you're, for example, using grams. So what we've been doing so far in dealing with these static or dynamic equilibrium situation is we've been saying, well, if there's no acceleration, if the object is moving at a constant velocity, or even more simply, if it's motionless, then the sum of the forces is going to be zero, right? And we can then think about summing forces either for all dimensions or one dimension at a time, knowing that they have to balance each other out. So if you look at this drawing of a box on a table, if we assume that the length of each arrow is representative of the magnitude of the forces, we have a frictional force and some applied force that are equal and opposite. We have a normal force and a gravitational force, weight, that are equal and opposite. The sum of the forces on this object, at least visually, looks like it would be zero, which means it's either moving at a constant velocity or motionless. And in the cases that we've been looking at, usually it's motionless. When there is acceleration, and you saw a little bit of this when you were using the simulation a couple weeks ago, but when there is an overall force, Newton's first law says that we're going to have acceleration. The magnitude of that acceleration is going to be proportional to the overall force on the object, the sum of the forces, and it'll be inversely proportional to the mass of the object. So more massive objects will accelerate less for any given overall force, and objects will accelerate more rapidly if you increase the overall force acting on them. I like to think about Newton's second law set up a little bit differently. I like to think about it like this: the acceleration of an object is equal to the sum of the forces divided by the mass of the object. That's an easier way to think about it in terms of kind of cause and effect. Mass is a property of an object. The sum of the forces is the cause of acceleration, and the acceleration itself is some effect that we're measuring. But mathematically, it turns out it's usually easier to solve problems if we set it up the way that it's written over here, because this is going to allow us to set up an equation that just looks a little bit more straightforward. Mathematically, it works out the same no matter how we do it. One thing to remember is that when we are dealing with forces, those are vector quantities. Acceleration is a vector quantity as well. the direction of the net force and the direction of the acceleration will be the same. The sum of the forces, um, it will have only one direction associated with it. There's going to be some overall force in some direction. That will also be the acceleration of the object that we're investigating. Um, the math that we're going to be using, of course, is vector mathematics. And so we're going to keep it simple today by not dealing with angles, but ultimately we're going to have to be able to use our vector solver um, to piece together components of forces. We're going to have to be able to use at least a little bit of trig in the absence of the vector solver to be able to think about components of unknown forces. And we'll try to simplify that and set up a system so that even if you're a little unsure about how trig works and how to make predictions about exactly how these things would be set up, we'll have a system so that you'll be able to relatively painlessly look at forces and break them up into components. I've mentioned several times that our ultimate goal here is to have a process that we use to think about solving problems involving forces and acceleration. And here it is. And I had a student teacher several years ago who was very interested in basketball, and he liked Joel Embiid, who plays for the Philadelphia 76ers, and his nickname was The Process. So we decided that we were going to call our system for solving Newton's second law problems The Process. And it works like this. So first of all, just like with kinematics, you should always start with a drawing. Super helpful. And the drawing doesn't need to be incredibly accurate, but it also should be somewhat separate from your free body diagram, because in a drawing you can see all the objects that are interacting. So if we had a problem where there was a skier going down a hill, for example, our drawing would look like this, right? Once you've got the drawing, make sure that you kind of think about, well, how am I going to arrange my x and y axes? So set up a reference coordinate system. Usually that's going to be relatively straightforward. We either are going to use a standard coordinate system where we've got horizontal and vertical, or you're going to use a coordinate system where one of the axes is lined up with the acceleration and or motion of an object. Sometimes we just can't do that. Sometimes the object is moving one way, it's accelerating a different way, and none of the forces line up with anything. There's and we end up needing to just do a bunch of trigonometry to try to figure things out. But typically, if we align our reference axes with potential motion and acceleration, it's going to minimize the amount of extra work that we have to do. Okay. The next step is to draw a free body diagram, and we'll look at this in a little bit more detail down the road in terms of specific steps for drawing a free body diagram. But essentially, we've talked about it before. What you want to do is just make sure that you have the object simplified and alone, and then you identify all the forces and draw them as arrows pointing away from the object. If you have forces that are not aligned with one or the other of your reference axes, you need to break them into components. So you have to look at all those forces separately. So if you have one force that's not aligned with your reference axis, you only need to break that one into components. But if you have three, then you have to think about all three of those forces as having both an x and a y component so that we can deal with them mathematically. And then we're going to use Newton's second law sometimes twice. Once for one of our axes and once for the other axis. Sometimes we won't have to do that. Sometimes there will only be forces in one axis. Sometimes we will have forces in an axis that we just won't care about. And so we may not need to use Newton's second law in one of our axes, not because there's no forces, but because they just don't really affect what we're trying to figure out. But there are going to be times when we need to use Newton's second law twice, once for one of our axes and once for the other. And then once we've set up our equations, we use those to find the unknowns. And there's a couple little tricks to this. One, and I think probably the most important, is that when we are using Newton's second law, we are going to consider all forces as positive numbers. So any variable that represents a force will be positive. In other words, if you tell me that some applied force is 5 newtons, I don't know what the direction of that is. Okay? And if we want to know what the direction is, then we're going to put a negative sign in front of the variable. So if our applied force is in the negative direction, we'll put a negative sign in front of our applied force. That will end up resulting in a negative value that we use in our equations. But the force itself is always going to be considered positive. So when we set up our equations, which we'll do in just a second, you'll see how that plays out. So here's an example. We have a block being pulled along a level table. It's accelerating at a half a meter per second squared. There's a force of friction on the block of 2.1 newtons. It has a mass of 3.8 kilograms. There's no other forces, so what's the magnitude of the pulling force? So we'll draw a picture first. So we've got a table, and we've got our box on the table, and let's say it's being pulled to the right. And that's it. We don't have anything else going on here. I'm going to add that the acceleration is 0.5 meters per second squared. And we can assume that that force is to the right for reasons that we'll see in just a second. It has a mass of 3.8 kilograms. That's pretty much all we know. So now I'm going to draw my free body diagram. And I know that my free body diagram is going to be opposite the direction of motion. So I'm going to assume that it's being pulled to the right here. And so my pulling force will be to the right. That means my friction force is going to be to the left. And it is possible for you to pull on something as it's moving away from you. If you came up to an object that was sliding down a hill and you wanted to try to get it back up the hill, you might grab onto a rope and pull on it. If somebody was sliding on a sled down a snowy hill and you grabbed onto the rope, it wouldn't immediately reverse direction and start going up the hill. You'd be pulling on it as it went down the hill. Ideally, you'd slowly stop it and then reverse its direction. In this problem, the description that the block is being pulled along a level table implies that it is moving in the direction of the pulling force. So that means the frictional force is in the opposite direction. That means it must be accelerating in the direction of the pull. And actually, it could be accelerating in the opposite direction. But again, the context of the problem makes it sound like it's speeding up. So if it's speeding up, it has to be accelerating in the direction of the pull. There's a force from gravity pulling straight down, and there's going to be a normal force from the surface of the table pushing up on the block. So there's my free body diagram. I am using a standard coordinate reference frame where up and to the right are positive. And there's only one object that I really care about here, which is the box, so I only need to draw one free body diagram. And now I'm going to resolve forces into components, and that's easy because all of my forces already align with my reference axis, so I don't need to do any trig. And that's how we're going to keep things simple today, is we're not going to have to deal with any trig. But we do have to apply Newton's second law in both the x and the y directions. So here's where we are going to use two separate equations. We're going to use subscripts to keep things straight. The sum of my x-axis forces will be equal to this object's mass times the x component of its overall acceleration. The sum of this object's y-axis forces will equal its mass times its acceleration in the y dimension. The horizontal forces are my pulling force, which is positive it's not positive, all forces are positive, it's in the positive direction. So I'm just going to write my pulling force without using a negative sign because it's in the positive direction. And the force of friction, which is in the negative direction. So I'm going to put a negative sign in front of the variable. My friction force is a positive number. When I put a negative sign in front of the variable, that means that mathematically it's going to end up being subtracted from any other horizontal forces. That should equal the mass of my object times its acceleration in the x dimension. In the y dimension, I have the normal force in my positive direction. The weight of the object, the gravitational force, is in the negative direction. That should equal this object's mass times its acceleration in the y dimension, and that is going to be 0. So actually, we can figure out some stuff here real quick in the y dimension. We know the normal force has to be equal in magnitude to the weight. There's no acceleration. We're trying to find the magnitude of the pulling force. These two forces, the normal force and the weight, are totally immaterial. So I'm not even going to bother finishing this part of the equation. It just doesn't matter for this particular problem. In the x dimension, we're trying to find the magnitude of the pulling force. So if we do a little algebra, we can see that the magnitude of our pulling force has to be equal to the mass of the object times its acceleration in the x dimension plus the frictional force. And I'm not going to do that math either. We know the mass, we know the acceleration, we know the force of friction. Those are all solvable. This is now a solvable equation, so we could easily come up with a quantity that would be in newtons that tells us the magnitude of the pulling force. So this is the kind of work that you're going to be doing today, the setup that you're going to have. And I want to make sure you understand. Don't get up and start setting this up yet. Before you set anything up, make some predictions, okay? But ultimately, your setup is going to look like this. You're going to have a supercart, and it's going to be attached with its hook to a string that's threaded over a pulley, and then a hanging mass will be suspended from that. All right, and the supercart is going to have 4 of those heavy metal bars on top of it. That will give the whole thing, the supercart and the bars, a mass of 2.285 kilograms. The supercarts have a mass of about 0.285 kilograms, and each of the bars has a mass of about half a kilogram. Okay, and then your track is going to be level, so you're not going to have to deal with any angles here. You want to accelerate this cart. It's going to speed up to the right at a rate of 0.1 meters per second squared. So we want our acceleration to be 0.1 meters per second squared. And we have a known force of friction of 0.02 newtons, which is super small. And I don't know what the real force of friction acting on the supercarts is, but it's relatively small, right? It's not super large. And then, so you're going to use that information to first predict the pulling force. That's the magnitude of this force to the right in the string. So you're going to try to predict that. And then, next, you're going to try to predict the mass that you would need to add hanging off the pulley in order to achieve that same acceleration. And this says 0.2 meters per second. It should say 0.1 meters per second. And by the time you see this, that will be corrected. And then once you've got that prediction about how much mass you need, then you're going to set it all up, use the supercarts to test it. So again, don't set things up until after you've made your predictions. The prediction is essentially 2 steps. Step 1, figure out what the force is going to be. And step 2 is figure out how much mass you need to get that force. And the trick is, and those of you who are in AP have seen a theme and variation of this already, the trick is that the weight of the mass is not the same as the pulling force. You're probably gonna, like, your brains are gonna make you feel like that's got to be the way that it is. Your brains are going to make you say, well, whatever that mass is, it's going to have weight, and that is the force that's pulling the cart. And it is true that the weight is kind of driving the whole system, but the weight and the pulling force are not the same because there's acceleration. If this system were in equilibrium, if there were no acceleration, then it would be true that the weight of that hanging mass and the pulling force on the cart would be the same. But that isn't true, which means we're not going to have a pulling force on the cart that's equal to the weight of the mass. And so that's going to be the trickiest part for you to work through in the predictions. And then once you get your prediction all worked out, then it's going to take a little bit of trial and error to get your tests and to really try to get some good solid data that matches up with your prediction.